This is the third lesson on reciprocal trig functions, and it will cover identities. Here are the starter questions. The first one is Year 12 question, and the second one is Year 13. You've done it more recently. Here are the mark schemes. And here is an additional question. This is optional, but it's quite a challenge. So here are some hints, and here's the worked solution. Right, so it's helpful to remember the two trig identities that you learnt in AS, and these are tan is sine over cos, and cos squared plus sine squared is 1. We call that second one, this one here, is a Pythagorean identity, because if you draw a little right angle triangle, you use Pythagoras to obtain this identity. They're going to be very useful today. So here's a little bit of revision. We're going to be doing some multiple choice questions, so you may need to pause the video quite a lot, or you could do this on the accompanying PowerPoint. So see if you can figure out the answer and predict what it will be. This gives us a massive hint. So there we go. See if you can predict the answer. Another big hint. See if you can predict this answer, a little trickier. Okay, so whenever we see some squared trig functions, we're thinking of the Pythagorean identity because it contains squares. It's a handy thing. Okay, this one's a bit trickier. If you notice, we've got a difference of squares in both the numerator and denominator. So, because if you could have sine squared, that gives you sine to the power of 4. Okay, so think about that first, and then you'll need your Pythagorean identity, and hopefully you end up with this one. This time we have mixed trig functions. There's a tan in there, so you're going to use your tan identity to help. Here's the answer. Again, mixed with a tan. Hopefully you recognise this. And now we're going to use the reciprocal trig functions. If you've got a whole bunch of mixed trig functions, it's really helpful to write them all in terms of sine and cos, and depending what you're aiming for, possibly tan, but usually just sine and cos. This one's a tricky one, see if you can figure that out. It's a new identity. Okay, let's see where it comes from. So because tan is sine over cos, and cot is the reciprocal of tan, if we just take the reciprocal of sine over cos, we get a new identity, okay, that you need to learn. So the next set of questions are going to make use of this. See how you get on. The input has changed this time. Okay. We have to match that input in our identity. Again, lots of functions, so it's often easiest to write it in terms of sine and cosine. And there we go. We've got a negative theta as an input for tan here, so the best thing to do is to think about what it would be in terms of the tan graph. So where would tan of negative theta go? Thinking about what tan of theta is. We have to write it as a positive one. Here we go. So we have a mixture again, so we want sine and cos, but also we have a squared. Here's the answer. A mixture and a fraction. We have a little trick when working with fractions. If you multiply the same top and bottom, that's just like timesing 1, so that's okay. Okay, so we're now going to prove some new some identities based on what you've learnt about cot and your other identities. if we're proving identities, like in a show that question, we need to work all the way from one side to the other. If you work from both ends inwards, you might end up proving something like cos theta equals cos theta, or 1 equals 1. So if we want a complete proof, we go from one side to the other. We usually pick the messiest side to start from, or the one where you know you can start. You've got a first move. However, if it turns out that doesn't seem to be working, you can try starting from the other side, and then we have a nifty little trick. If you start from your first side, you get stuck, you have a go from the other side. When you get to the point where the things match, then you just reverse the order of your second set that you're working out, so that you end up with a proof that goes all one way. And for the following questions, these tend to be my solutions or ones from examples, and it might not be the only way of doing it. Okay, I think the left-hand side here is messiest. We've got lots of different functions there. We've got cot, so remember our new identity for cot. So this is using our old ones, or I would probably go straight for this next item here, where we've got cot is cos over sine and sec is 1 over cos. And if you cancel out those coses, you get 1 over sine, and you know that is cosec. Remember, the third letter of your reciprocal trig will give you what it's reciprocal of. You have a go at these ones. Here are the solutions. Okay, we have some fractions. Deciding which side is the messiest, I think the new one with all the cots in it. Okay. Right, we are aiming for tan. So normally I'd think cot is cos over sine, but because we're aiming for tan, we might as well write cot as 1 over tan. Okay, so let's do that. Now we've got a fraction over another fraction, so it's a bit of a mess. A simple thing to do is to get rid of all those denominators, okay, by multiplying top and bottom by tan over tan, which just has the effect of timesing by 1, so that's allowed. And if we do that, it's the one that we're after. Okay, you have a go at these ones. Here are the solutions. Okay, next one. Right, it's a bit tricky to choose which is the messiest side. For the one that's a subtraction rather than multiply, they tend to be easier. Right, so again we've got different trig functions on both sides, so it seems sensible to do everything in terms of, in this case, cos. There we go. We have two separate terms, one of which is a fraction, and we could write the second term, we could write that as like over 1. Okay, so if we've got that, we then combine the fractions. If you have a single fraction, you split them up. If you have separate fractions, you combine them. So we're combining them in a subtraction. And this is what we get. We have to multiply the right term by the denominator cos. Okay. Now this should hopefully ring some bells. We've got a squared term there, and we know the lovely Pythagorean identity. So that gives us sine squared over cos. Right, now I'm a little bit stuck. That doesn't look like tan A sine A. So let's just have a think of the right hand side. Let's mess with that for a bit. So I'm going to replace tan with sine over cos. And there we go. That looks a lot better. If you multiply those two sines together, you get your sine squared. So we've pretty much matched up. So I'm now going to kind of reverse the process. I'm going to write this one down next. Okay, and then sine over cos is tan, and we get the right answer. You have a go at this one. Here's your answer. Another one. I think the side looks messiest because the left hand side is a fraction, but you've just got some nice sines and coses. So let's see what happens. Okay, we've got lots of different trig terms, so we want to replace those with sines and coses. There we go. Right, we've got two fractions. We can add those fractions together. Now, It looks kind of similar to where we're aiming for, but it's not quite the same. It's really annoying. These are really simple terms. There are no squares. Okay, we like squares because we can use the Pythagorean identity. Okay, so if we look at this 2 term here, if we multiply everything by 1 minus cos A, we're going to get a difference of squares. So it's a little bit like when you're rationalising surds with 2 terms in it. You multiply by the same thing but with the opposite sign, and that's going to create for a nice squared, which will hopefully give us a Pythagorean identity we can use. So if we expand that out, get difference of squares on the top, we like it. There we go. 1 minus cos squared, we know it is sine squared. And now, I haven't multiplied out the denominator because it didn't look like it was going to make it nicer. In fact, it's been good we kept it factorised, because now we can cancel the signs. And we get... However, you might have thought that this fraction side was messier. So let's look what the thinking is if you started from the left-hand side. Okay. Right, so starting from the left-hand side, it looks very simple, doesn't it? So there's no squared terms and there's nothing to convert into sines and causes. So there's no squared terms, so we're going to introduce one. So again, we look at the 2-term denominator there, and we're going to create a difference of squares by copying it and putting a plus instead of a minus, and multiplying top and bottom by that to keep it fair. Okay, so you can see now we've got the factorised version of a difference of squares, so that is going to play to our strengths. What we want to do, use the Pythagorean identity. So 1 minus cos squared is going to be sine squared, and now we can cancel out. Okay, now we know that we got to here before, and this again is looking very simple and not like what we're aiming for. But if we have a single fraction, one option is to split it up into 2 parts. Okay, so over the same denominator. Now we know that 1 over sine is cosec, and cos over sine we have now learnt is cot. So we get the answer. So we're now going to develop our Pythagorean identity and see if we can come up with something else. You now know how to get what reciprocal trig look like, so we're not frightened of dividing by cos. So we divide everything in our lovely sine, cos squared plus sine squared is 1. We're going to divide it all by cos squared and see what we get. So for our first term, these cancel out and we get 1. For our second term, well, sine over cos is tan, so sine squared over cos squared is tan squared. And 1 over cos is sec, so 1 over cos squared is sec squared. So this gives us a new identity involving one of the reciprocal trig functions. What if we started instead with our cos squared is 1 and divided by sine squared instead? There we go. Let's think about each term. So we know that cos over sine is cot. So cos squared over sine squared is cot squared. Sine squared over sine squared is just 1. And 1 over sine squared is going to be 1 over cosec squared. So there's a second new identity from the old ones. Remember that sec squared x just means sec of x all squared. Okay. Now, one way to remember the right-hand side one is that it's all the c's, apart from our original lovely cos. Okay, so it's all the new c's. Okay, as long as you're pretty good at not mixing up like which side the +1 goes on. So I can't remember it. I always mix them up in my head. So every time I just, like at the start of doing a paper on these or an exam maybe, I would jot down sine squared plus cos squared is 1 and derive them by just dividing a set by sine squared or dividing a set by cos squared. It's up to you. If you're good at memorising, brilliant. If not, derive them. Okay. You're expected to know these and know when and how to apply them. So let's have a go. Okay, oh, here's a summary before we have a go. These are strategies we've been using. This is just for reference in the PowerPoint. Okay, right, finally, some questions to try. So we notice we've got a squared term. And at this point, you won't have had time to memorize. So you're looking for the Pythagorean identity that involves sec squared, and it's the one with tan. So there's the answer. Okay, the same again. We have a squared, so we're thinking one of the Pythagorean ones. So we have a look at our list and we look for cosec. There we go. And that's the one with cot in it. But the +1 is on the wrong side. So this is the danger. We've got to be careful we don't mix up which side has the +1. I suppose the t looks a little bit like a +1. So you could kind of remember it from there. Okay, 1 plus tan theta. This is a good one for identifying if we've misunderstood square roots. Okay, so we're thinking there was one of those identities had a 1 and a tan in it. Okay, but it was a tan squared. So perhaps you might think, well, if we square root it, we're going to get sec. Now that's correct, but we can't split up these terms. We can't have root 1 plus root tan squared. Because remember, you can't split up inside a square root. You can't split up when they're adding. You can when they're multiplying. So it's none of the above. Okay. So we have lots of brackets that we could expand, but also there's going to be some squares. So we're thinking about those Pythagorean identities and the one with some tan squares in it. Okay, so that's the sec. And we get this for our answer after a bit of work. Okay, again we have some brackets to expand out, and there's going to be a cot squared. So we're thinking about the identity with cot in it, cot squared in it. Okay, and this is the answer. Alright, a fraction, we have some squared terms. We've got both the tan squared one and a cot squared one. So let's look at our identities. Okay, and see how we could apply those. And then we're going to have a simpler fraction. Okay, and so it might be handy to write it in terms of sine and cos if you're working through this on paper. And you're involving some fractions, and this is what you should get. Alright, well there's something rather lovely at the top there. And then we need the Pythagorean one because it's got a squared in it for cos and cot, cosec, sorry, and cot. Alright, I've written the other ones there. They might come into play later. Alright, a similar idea to the previous question. You need your Pythagorean identities. You can see at the top we've got sine squared. The one that involves sine squared is the one you learned in year 12. Then we need the one with cosec and cot in it. Okay. Similarly, again, you have a go. Right. Now there's a bit more work on that. There we go, and there's your answer. Right, let's have a look when we've got a more complicated set of fractions. So definitely the left hand side here is the messiest side. We've got to show that messiest side all turns into 1. Okay, so first of all we've got separate fractions, so we can turn them into one fraction by adding. We will need a common denominator of tan theta, sec theta, cosec theta. We need to multiply top and bottom on the left by sec theta, cosec theta, and top and bottom on the right with tan theta. Okay. Now we've got loads of different functions here, so let's think about writing things in terms of sine and cos. So we've got sine and cos, and then sec is 1 over cos, and cos is 1 over sine, so they're going to cancel in that first term. Okay. And now we've got a squared thing, tan squared, so we look up the identity, or remember the identity, with the tan squared in it, and that's great, that's going to simplify matters. Now I hadn't bothered messing with the denominator yet, and that's a good thing, because one of the sec squareds can cancel with sec. Okay, right, but now we still have lots of different functions, so I'm going to replace them all with sine and cos. Okay, now on this denominator here we can see that the fractions involved, we can cancel those signs. We get the same on the top as the bottom, so that's just 1. Okay, right, this one is a bit of an odd one. We're going to start with the left hand side. So the right is just some brackets to expand. That looks nice. Okay, and you'll get a difference of squares, but then we've got a difference of squares equals the difference of squares, and it looks a bit confusing. So we're actually going to start with the left, because we'd have to go from this sort of point anyway on the right. So first of all, we've got some squareds. We've got our Pythagorean identities. We can substitute those in very carefully using brackets to make sure we don't make a mistake with and take away the negative. Alright, so that simplifies to be tan squared minus cot squared, and that is now heading towards this bracket territory. It's a difference of 2 squares, so we can factorise. Okay. Right, a different structure this time, so we're an expression for x, and then we need to substitute into this expression and simplify it. So literally just popped in x is sec a plus tan a, and 1 over x is 1 over sec a plus tan a. Right, again we've got 2 terms, one of which is a fraction, so we can imagine this one is over 1. We want to add those fractions. If we do that, we'd need to multiply the sec a plus tan a by the denominator sec a plus tan a, so it's allowed to be top and bottom. Okay, then we've got some brackets to expand. Here we go. And now we have some squared terms. Okay, we need the Pythagorean identity, because we've got squareds, involving sec and tan, and we can see this last term matches exactly the sec. Okay, so we've got some matching terms there. Let's group them together. And now you can see there's a sec in every term at the top, so we could factorise that, which is super, because our numerator and denominator have got the same factor, sec a plus tan a. We can cancel that, and we get what we're aiming for, 2 sec a. Right, here are a set of questions for you to have a go at. I'm going to give you the solutions. Okay. And here are some exam questions which kind of cross into the territory that we were looking at in the first lesson, where when we are given some information about one trig ratio, we're asked to then find another trig ratio. Notice in question 1 it says they're acute angles, and we know that all of the different functions are positive when we have acute angles. Okay, but for number 2 it just says find the possible values of, so it doesn't say whether you're obtuse or what, so you have to include all the options. Alright, here are the mark schemes. Right, and another exam question. This one's quite challenging. Okay, so we start with one equation and we have to transform it so it turns into this lovely quadratic in cosec. So you can see there's some squareds there, so hopefully you're thinking about what that implies you need to do. Okay, once you've got that lovely quadratic, you can replace this equation with the quadratic one, which will help you. You can solve it on your calculator for cosec. Think very carefully about what values are allowed for cosec. Think of that graph that you did the other day and the range that you're allowed for cosec. Okay, and then once you've got one, you can draw a little triangle, and that will help you find tan. You're told that x is obtuse, so you might want to use a cast diagram or a graph to help you with your signs. Here are the solutions. Right then, these are really challenging questions, and so they're just optional. I'm not going to go through them in detail. Here's a hint. and some guidance towards the solution. Here's the answer. Okay, and a hint for number 11. Alright, and if you work through that, it should look like this. Get 198. And this is just additional practice if you want it. Okay. Here's more. And here are the solutions. Well done.